Welcome back to HackCode. In this video, we're tackling an essential problem from LeetCode, Pacific Atlantic Water Flow. This problem is a fantastic way to master DFS traversal in matrix. We'll explore both the traditional 2D matrix approach and a more efficient solution using sets to track visitor cells. So sit back, relax, and let's dive in. So before we dive into this problem, let's look into what companies ask these questions. So it is asked by the top broad-based companies like Amazon, Bloomberg, Facebook, Google, Microsoft, and Oracle. So why not give it a try and crack this problem? So what is the problem statement? There is an M-crossed rectangular island that borders both the Pacific and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges, and Atlantic Ocean touches the island's right and bottom edges. So as we see, this is a rectangular grid. So this is just the island here, and the Pacific Ocean touches the left and top, and the Atlantic Ocean touches the bottom and right. Okay. So the island is partitioned into a grid of square cells. You are given M cross an integer matrix heights, where height of all C represents the height above the sea level of the cell at particular coordinate. So basically, this island is split into the particular cells, and each cell is a square. And what does the value of the cell represent? It represents the height above the sea level of the particular cell. Okay. Now what should we do with this height? So let's look into the problem to understand more. The island receives a lot of rain, and the rainwater can flow to the neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any adjacent cell to the ocean into the ocean. So basically what they're saying, this water can flow from cell in 4 directions, that is top, bottom, left, and right. And this flow happens only if these two cells are the same height, or even if it is a lesser height. Okay, and next is what? So all these cells which are having the border to the ocean, the water can directly flow into the ocean, right? So that's what they gave in the next step here. So water can flow from any cell adjacent to the ocean, okay? And next, what we need to do? We just need to return this coordinates from which the water can flow into the both Pacific Ocean and Atlantic Ocean. So we just need to find these coordinates and return this list of list. Why it's list of list? Because each coordinates is we represent as a list, right? And we had to return such list of the coordinates. That's why it's a list of list. Okay. So that's what we just need to return. The result is just a list of the coordinates from which the water can flow into the Pacific and Atlantic Ocean. So let's consider the example just to give us more idea. So here, this is the example where they're given us grid. So if we consider the 5 here, so from here it can go into this ocean and this ocean. If we consider 4, the water can flow into the Atlantic Ocean this way, and it can go here and it can reach the Pacific Ocean this way. And similarly 4 as well here. So it can go this way and it can go this way. So similarly, like all the cells, like water can flow in the same way. Okay. So basically you got the condition, right? So main condition is the water can flow in all 4 directions, given if they are same height or even if it is the lesser height. Okay. And we just need to return such coordinates from where the water can flow into the both oceans. Okay. An example 2, we have heights is only 1. So basically we have only one cell and the output is 0, 0. Basically this is the only coordinate we have, and from that coordinate the water can go into both oceans. Okay. And the constants here are m is equals to height length. So basically it is just like, if we take a matrix, m is nothing but the number of rows. Okay. And n is nothing but the number of columns we have. So here heights of or dot length. So basically this length is nothing but number of columns, right? So if we consider this list, we're just taking this length, and that's nothing but a number of columns. And here, what is this? This m and n are in the inclusion range of 1 to 200, and heights of RC is in the inclusion range of 0 to 10 power 5. So basically the value of the particular cell is in this range of 0 to 10 power 5. Okay. So this is the boilerplate code given, wherein we have a Pacific Atlantic method which takes the heights. Height is nothing but the list of integers, and it returns the list of integers. This list of integers is what? The coordinates from where the water can flow into the both oceans. Okay. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem-solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So let's look into the approach. So it's basically the DFS traversal. Okay, so what is the intuition here? We perform a reverse DFS. Start from the borders where water can directly reach the oceans. Mark all the cells that can flow into the Pacific Ocean and those that can flow into the Atlantic Ocean. The cells visited by both DFS traversal or the result. So let me just explain the intuition here. So what I'm saying is, so instead of checking from the center or some random point, what if we explore from the corners? If at all we need to perform the DFS from any center, how can we do that? So basically we need to compare the value of the cell with the 4 adjacent cells like this and this and this. So if the value of this cell is same as this adjacent cell, the water can flow, and even if the value is lesser, it can flow. So these are the two conditions, right? And it is not very definitive that which cell to start. So how about doing it in reverse engineering manner? So basically what I'm saying is we have to go to the corners. From the corners, it's evident that it would be going to one of the oceans, right? So basically this corner, the water can flow into the Atlantic Ocean, and this corner, the water can go into the Pacific Ocean. Similarly for these corners as well. So from this corner cells, what we can do, we can check if the water can reach the both oceans. That's very simple, right? So we're just starting from this corners. So from the corner, what do we need to check? We need to check if these two cells are in the same value, then the water can reach from here to here, right? Or else how can it reach? If this value is greater than this cell, then also the water can reach. So that's what we need to check, right? So if we can check these two conditions, then the water can reach this cell and it can go into the ocean. Okay, so that's what we need to check in a reverse DFS. Okay, so that's the idea when I'm at a reverse DFS. So we are doing this reverse DFS because we don't know where to start if we consider any arbitrary point. But if we consider this corner cells, it is evident that it can go into the one of the oceans, and we just need to check for the other oceans. So we start exploring from column, or we start exploring from rows. So basically we explore 0th row and last row, and 0th column and last column. So these are the things we need to explore for the both oceans. Okay, so let's look into the algorithm, which should make it more clear. Initialize the visited matrices. So create two matrices, Pacific and Atlantic, to track cells that can flow into the respective oceans. So basically we perform DFS for the individual oceans. Okay, and then what we need to do, we need to DFS from the borders. So that's what we discussed, right? So start DFS from the top and left edges to fill the Pacific matrix. So to reach the Pacific Ocean, what all cells we need to explore? We just need to explore these two cells, right? So top and left edges. And next, start DFS from the bottom and right edges to fill the Atlantic matrix. Basically for Atlantic matrix, we just need to explore these two edges, okay? And perform DFS traversal. So in each DFS traversal, move to the neighbors that have the height equal to or greater than the current cell. That's what we just discussed, right? So basically if the height is greater than the current cell, then only the water can flow from this cell to this cell, and then it can reach to the Atlantic Ocean. In step 4, find the intersection. So identify the cells that are marked as reachable in both Pacific and Atlantic Ocean. Then that's how we can get to know that the water can reach the both oceans, right? So basically from this cell, if we can reach to the Pacific Ocean and Atlantic Ocean, then it is clear that we can reach the both oceans. So we just need to find that intersection, okay? So that we can easily find using this matrix lookup, okay? So let's look into the code. It's very simple. So firstly, we saw that this is a boilerplate code given, and then in the boilerplate code, we just got the row length and the column length. If you look into the heights, what we have is, so this is given as list of list, and the length of the list gives the number of rows, and length of this particular element gives the number of columns, right? So basically this is number of rows. If you see, this is just rightly translating row, and then length of this is what number of columns. So that's what we're doing it. We're just getting the rows and columns here, okay? And next we are initializing the visited matrices. So this is just the list comprehension approach of initializing the matrices. So we are repeating this false for all the range in rows. So basically for all the columns we're initializing false, and we're repeating for this many rows. So this is just a shortcut form of initializing the 2D matrix. Same for Atlantic Ocean as well. And next what we have, we just define the DFS function with the base case. So for DFS, we just require the row and column and the visited. This visited is required because we are visiting the two oceans. Else we might just kept like row and column only, and visited would be the global variable, okay? So basically this visited is varying. That's why we kept a variable here. This is varying from Pacific to Atlantic Ocean, right? That's why. And the base case is what? If we visited that particular cell, we don't need to visit it again. That's why we just return it. So if you don't have a base cases, this recursion function would keep on calling itself and it give a recursion stack depth exceeded error. So that's why we should have the base cases to stop the recursion at that particular point. Okay. And that's what we do. We just mark the cell as visited. So since we visited the cell, we just mark it as visited so that we don't visit it again. And next we explore all valid neighbors. So we just define this directions. This directions is nothing but the X and Y coordinates for exploring all the neighbors we have. So if we consider this cell, so let me just put it here. So this is what cell we have, and then this is the X and Y coordinate. Okay, so from this cell, if you have to reach this point, what would be the coordinate? So let's consider this as 1, and this is 1, and this is -1, and this is -1. The coordinate here is what? 1, 0. And here the coordinate is 0, 1. And here it is 0, -1. And here it is what? -1, 0. This is what the directions we have represented here. And next what we are doing, we just explain all these directions. Okay, so I'm just grabbing this dr and dc. So this is just a row and column value, right? So I'm just calling it as dr and dc variables. And next we are forming the new r and c. So how we form that? We just add the r to the dr and then we add the c to the dc. Basically we have to increment our x and y coordinates, right, to get the new coordinate. That's what I'm doing here. And next what we doing, we check the boundaries. So we should check the boundaries, right, because it would go the out of the boundaries. So in that case, it would use the index out of bound exceptions. That's why we just need to check the boundaries and then only we have to visit. Okay. New row should be in the enclosure range of 0 and rows -1. So that's why I'm doing less than check here and less than or equal to for 0. Okay. New column could be ranging from 0 to columns -1. That's why I'm doing less than or equal to here and less than here. Okay. And next what I'm doing, the flow condition. The flow condition is nothing but we just need to check if the neighboring cell is greater than or equal to the current cell. So in that case only the water would flow from this cell to this cell, right? So that's why we just check this. Okay, so remember we're doing the reverse engineering here. That's why we're just checking it. Okay, so and then for this case only we perform the DFS. So we're just passing the new row and new column and the visited. Okay, whatever we got the visited, we're just passing the same thing. Okay, and this is our DFS function. And next what we're doing, we run DFS from the Pacific and the Atlantic borders. So to run for the Pacific left edge, we just iterate over the rows. Okay, so this is the Pacific left edge. So here the row is changing, right? The column remains 0. Okay, so that's why we're passing DFS of r comma 0. So this row is in the inclusion range of 0 to rows -1 here. Okay, and next Pacific, this is the Pacific matrix. And next what we're doing, we're checking the Atlantic right edge. So this is the Atlantic right edge. So here the column is same, that is cols -1. So this is just the maximum column we have, and then r column -1. So here we're passing r cols -1 and Atlantic. Okay, and next what we're doing, we're exploring the Pacific top edge and Atlantic bottom edge. Similarly here as well, the row is same and the column keeps varying. That's why we are exploring for C in range of 0 to cols and the row remains same here. And we are considering 0th row and last row, which is rows -1 here. Okay. Now we finish the DFS and we just need to check for the intersection and store the result. So that's why I initialized the result list and then we're just iterating over the matrix for R in range of rows and C in the range of cols. We're just checking if the same cell is visited in both Pacific and Atlantic traversals. That means we can reach both oceans from that particular cell, right? That's why we just append this to the result. Okay, and then at the end we return the result. Simple, right? Plus you can do complexities. The time complexity is O of mn, as each cell is visited at most once during the DFS traversal for each ocean, and the space complexity is O of m cross n. This is the space required for the Pacific and Atlantic matrices and the recursion stack in the worst case. So basically each matrix is O of m cross n space and the recursion stack would also take the O of m cross n. Okay, so it is 3 into O of m cross n, but 3 is a negligible factor, so that's why it's O of m cross n. Okay, so I got the code ready here. Let me try running this. So this is the accept solution for the two cases. Let me try submitting this. So cool, this is the accept solution for all the test cases and beats almost 75% of the users. Let's explore this solution using set. So basically here what we're doing, we will be using set in place of the 2D matrix. So how is this helping us? So basically this would be more optimal in terms of space. This is because we don't need to initialize the whole 2D matrix. We just keep on adding the cells which we visit, right? And we might not visit all cells. So here the space complexity would be optimized because the space complexity would be up to O of m cross n. That not necessarily that it would always be the O of m cross n, because in the worst case only we would visit all cells, right? So in the best case we would not visit all cells. So that's why we don't need to instance the whole 2D array for that, and we can keep track using the set only. So in this set we just store the row and column value, that is just the coordinate value. Okay, so that's the only difference here. So we just instead using the set here, there it was a 2D matrix, you see, right? It's a 2D matrix. We just instance false for everything here, but we just use the set here. Okay, and here this remains same. We just pass the visited here. Visited is what set here. So here how do we check if it is visited? We just see if R and C is in the visited. So there it was just a boolean check, right? So we were checking if visited of RC, that means we are checking this is already visited. If it is visited we would have marked it true. So here if it is visited we would have put that into the set. That's why we're checking if R and C is there in the set. Okay, so here if it is there in the set we just return it. Okay, and that's one difference. And next what we do, in place of marking this as a true, we just add into the set, right? So that's why we're just adding into the set. Okay, and next this is same as previous approach. This is the directions we have, and here also we just check the boundaries and flow condition. So this is same. Okay, And next we just perform the DFS, this also same. And next this step, this is where the difference happens. So here we just do the AND. So basically AND can give the intersection of the both cells, right? So if the cell is present in the both sides only, then we would get that in the result of the intersection. And what we are doing, we converting that in the list, because we just need to return the list of list, right? Not the set. That's why we convert in the list and then we return it. Okay, so here we can directly return the list of Pacific Ocean and Atlantic Ocean. I just kept the additional variable to have it more clear for you, okay? Else we can directly return from here. So I got the code ready here. Let me try running this. So this is accept solution for the two cases. Let me try submitting this. So this is accept solution for all the test cases and beats the 70% of users. Cool, right? And that's a wrap on solving Pacific Atlantic water flow using DFS. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.